Swayam Prabha. Digital India. Educated India.
In this lecture, we will be talking about reinforced soil, its principles and mechanisms. As I just mentioned, in the ground improvement, we have the use of inclusions. Inclusions means whatever, say for example, a steel rod or anything that can be introduced to give a reinforcement effect that helps in increasing the bearing capacity, reducing the settlements and increasing stability in whatever manner you want and all that. So, this is one of the significant aspects in the soil mechanics, where reinforced soil has proven to be a very useful technique in many geotechnical problem solving approaches. I would like to just introduce what is this stabilization, and stabilization by external means, and what is stabilization by internal means. We are all familiar with retaining walls, say for example, cantilever walls or gravity walls and all that. There is some force acting, say because of earth pressure or because of the earthquake force and all that. We try to reduce that or nullify that force by putting some sort of material, say for example gravity wall. The weight of the gravity wall itself will take care of the pressure acting. So, we use an external system. You have a soil creates a pressure. To withstand that pressure, we have a gravity or some sort of retaining system which can stand against that forces. What we do is that we try to the other way of handling that is that you have a soil that is creating pressure. So, put some sort of reinforcement inside, because of which all that forces that are coming onto that retaining system are minimal or negligible, and to that extent that it is very stable also. So, what we say is that this is an externally stabilized system, and the other one is internally stabilized system, in which you have reinforcements introduced, and they intersect the failure mass and failure surface and deflect the failure surface beyond higher beyond certain failure zones, and there will be higher shear resistance mobilized along the failure plane, and that helps in having higher factors of safety. So, for example, there is say you excavate 1 meter of soil, and then what happens is that if you excavate 1 meter of soil, there is a type of a wedge formation that can come. There is a tendency for it to slide. So, one way is to see that you put some sort of a member, external member, to see that that is stable. So, you should be able to calculate what is the horizontal force, and you should see that you should also calculate so that 1 meter excavation some weight that can stand that horizontal force. The other way is that you do not allow that force to develop, put some reinforcement inside, so that the force coming onto the external surface or the outer surface is minimal. So, this is what we do. Like just some examples of the externally reinforced soil systems, like we are familiar with cantilever walls or even gravity walls like this, where you have say for example, you have a potential failure surface, and then you design all this retaining wall for the weight of the soil here, then the earth pressure acting here and all that. And what we do is otherwise that we have a braced excavations. Sometimes this is a failure soil, failure mass, then we put some sort of braces, like you have a collapse, say you must have seen for pipe the digging, for the pipelines. So, there may be 2 meters of pipe you would like to put there. So, you have to just excavate a little bit of 2.5 meters on either side, and 2 meters pipe you are trying to place there. So, that excavation should not cave in. So, you try to put some sort of struts like this, tensile members, and then at the bottom also like that, you try to create some system where this retaining wall is stable. The other way is that you try to put some there are this is what we call externally stabilized systems. The other way is that we see that you have a tied back, like this is a failure mass, we know this is a weight of the failure mass. We try to put some sort of anchors here, and these are all tensile elements. We call them as tie backs. Tie is a tension member that we know, and the tension member holds this wedge. Say the two reinforcements in this wedge will hold this thing, and this we anchor it here. This is called anchor. Anchoring means holding it, like this is a tensile element and then it is hold here, because there is a bond resistance is higher here, it is held here. Then once you do like this, then the pressure coming on this is quite less. So, it is an in situ wall. This is called tie back wall. The second thing what we do is that same as it is actually nothing but the reinforced soil, like we are trying to put all these reinforcements in such a manner that the earth pressure, say for example Ka gamma h or K naught gamma h, whatever, depending on the state of the soil, whether it is close to earth pressure, active earth pressure, or it is K naught. Okay. Say for example, if the depth is not going to be very high, it will be K naught, but if the depth is going to be large, there is a tendency for the soil to be in active condition, and then there is a movement. When the moment there is a movement, that the pressure gets released. Okay. So, this is what is called reinforced technique, in which say you try to if there is a failure surface, you try to put all these sorts of reinforcements, and this is one. Actually, you may wonder why there are only 2 members here, there are many numbers here. The difference is that actually the here the tensile force requirement will be very high, but the same tensile force is distributed here. Okay. That is very important, and this is somewhat in terms of the construction, this is somewhat little expensive compared to this one. That is what people have seen. The other one, the most classical case that we have been very familiar with this is soil nailing. In the sense, this is a failure surface and you put a series of nails like this, so that the earth pressure is not developed. So, the moment the earth pressure is not developed, then you do not need anything here. So, put simply some sort of facing, and then it is all right. So, this is all called externally stabilized systems, these 3, and this is called internally stabilized systems. And over a period of time, we have seen that the stabilizing the soil using some of these techniques is much cheaper compared to this, and as you increase the height, say for example beyond 3 meters or 4 meters, or even say for example I was taking the case of 10 meters or 15 meters, definitely they are going to be 30% cheaper, is easier to do. And for example here as you the increase in height is there, maybe you have to go for counterfoot retaining wall, right. Here that distinction is not there, whether it is 10 meters or 20 meters or 30 meters, same technique, but you have to stagger it in some sense, so that it is the factor of safety needs to be calculated properly. How this soil reinforcement technique came is that actually it is people have been using this soil reinforcement for a time from the time immemorial. Like people say that even when you make Ganesha idols, you put some sort of fibers, so that the shrinkage cracks are not there and all that. Here the same thing, like this is a typical diagram. The soil reinforcement technique in the recent times was discovered by one Henry Vidal. He is actually a French engineer working in in LCPC France, where he went with his daughter to play on the beach, and his daughter is a quite young girl, and her job was to take the sand, construct a small heap like this, you see the heap, then jump on it. Then what happens, it collapses, right. But then what she does was that what she did for some time was that she takes all these sort of pine needles there, again jump. What happens, this will not collapse. So he finds it very interesting, and then he was wondering why this thing is happening. Like the thing is that You can even construct the base width. Say for example, we know that the soil angle angle of repose is say 25 degrees. So, which means that you can't construct a slope beyond 25 degrees. But in this case, if you put this sort of material, you are able to construct slopes up to 50 degrees, which is quite interesting. Then even the height is also more sometimes. So, for the same base width, height can be more, or you can the angle of repose can also be more. So, that is very interesting. So, then he finds it very very challenging, and then goes back to laboratory and then finds that the friction between the soil and say for example, the sand here is, and then the reinforcement is responsible for this stabilization. Why is that you have a higher angle of repose, or higher the height is more? He was able to understand that it is because of the friction between the soil and the reinforcing element, and then that leads to some sort of tensile force mobilization, because the moment there is a friction between the soil and reinforcement, there is a tensile force mobilization, and okay, as long as the tensile force is operating, like it is all right, it is stable. So, he after that he goes back to laboratory, does lot of research on many varieties of reinforcement elements, like it can be many things like steel rods, then strips, many shapes of metals and all that, and comes up with a design procedure to design retaining walls and to control landslides or the slope stabilization problems. In fact, the first applications of reinforced earth technique was in 1966 or 1969, when the first wall was built. In fact, you can see some of these figures in my book, which is on soil reinforcement and geosynthetics, and where the first time they did this thing, and then they find it, he developed a design procedure. The design procedure is again very simple. We know that the retaining wall has to be safe against external stability, first external stability in the sense that bearing capacity failure, then sliding failure and rotational the overturning failure, all these things are there. That is a standard procedure. Now, you have a reinforcement element, and since you have a reinforcement element, it should not lead to stability. So, he was looking at so tensile, see the thing is now, as I just mentioned, the force, tensile force is mobilized. So, the reinforcement will have some tensile capacity. As long as this tensile capacity is more than the tensile force generated, the system is safe. So, that is a factor of safety, like say the tensile capacity is say 100 tons, and the tensile capacity in any member is say 50 tons. So, 100 by 50 is a 2 factor of safety, like there is a lot of capacity, but factor of safety is 2 now. Similarly, that material should not come out. So, for example, this is stable, but I should not pull it out. If I pull it out, what happens? The pull out resistance is low. So, even the pull out, the tensile force generated should have like as I just showed in the diagram, the anchoring, it should be anchored. So, it should have some it should not come out. So, that is called there should be sufficient length of the reinforcement. So, for example, if there is a short length and if it comes out, there is not it is going to collapse, it does not mean anything. Say for example, we have small fibers here, they may be little helpful, but it is not going to be so much helpful. So, this is one important thing. So, he finds that actually this is the origin of the reinforced soil technique, and after that he developed that, as I just mentioned, went back to the laboratory and perfected this technique. This is another small example. You put some layers of reinforcement in anything and you just stand on it, definitely this becomes like this. You can't say already can see that his leg is embedded in soil, and they have equal height, weight, volume, everything is same, except that you have a reinforcement here, everything is same except that they have a reinforcement here. You can see that it is able to support his whole weight, but here it is not that. So, this is actually why is it, because this reinforcement element is taking care of the friction. I will just show you that. You can see in this figure that, see, you have an element and you apply some load sigma 1 and it attains equilibrium, it goes to sigma 3, right. So, you have vertical displacement delta sigma v, then horizontal displacement delta sigma h by 2 on either side. Okay. So, this is in the case of unreinforced system like I just mentioned, like this. You have a system like this, and what happens, the moment I put the reinforcement, there is an applied load like this, it starts acting like this, then there is a resistance here, the opposite direction. So, it does not move at all, not so much, there is a small movement, but the thing is, to generate friction, it has to little move, little small movement is required. You can just see that it is delta V R, delta H R by 2, it can be very small. So, but then you can see that there is a it does not collapse at all, like we have seen that particular figure. So, this is a principle of reinforced soil, in which there is what is called this reinforcement. It is like you are applying extra pressure, confining pressure on the other side, so that whatever is a vertical force, there is a lateral force that is coming here, right. So, that much, that is what is I meant by pseudo confining pressure. So, there is because of the friction between the soil and reinforcement, some sort of pseudo confining pressure is introduced, which makes the system stable, unlike this case where there is a total collapse, right. So, this is a very simple principle, and to operate it very effectively, some more requirement is there, that here another example, like suppose the soil, as I just said, it is at rest, so this is actually, this is a Mohr circle, this is a normal stress, this is a shear stress, and this is a friction angle of this, and actually this is as long as in the previous diagram we have seen that there is a vertical force and then there is a confining pressure developed, which is nothing but, as I just said, extra confining pressure, which you can say is K naught times sigma V, lateral stress is K naught times sigma V. So, as long as K naught is there, K naught means at pressure at rest, the soil does not move. But as the moment there is a small yield, like if say for example, if the pressure increases, there is an yield, what happens? So, this is actually this is say sigma 1, K naught or sigma V, this comes like this. So, as long as the Mohr circle is here below this line, there is no failure, right. So, you apply some more force sigma V, it again mobilizes equivalent pseudo confining pressure K naught sigma V, like I may just increase the sigma V, and then again there is one more circle that can come here, and it can K naught sigma V. So, as long as the circle is within this, below this line, it is safe. But then there is also a possibility of little yield, if there is a friction between the soil and all that, it may touch this thing. So, essentially our objective is to see that these two conditions, like essentially it should not or it can even get chopped off, tensile failure, it can, because you keep on applying higher normal stress. Say for example, if there is a slip circle here, like you keep on increasing K naught into sigma V, then the failure surface, if it is within this, it is all right. But if it touches and then there is also a little bit of yield, then it leads to some sort of it may touch this line. So, our objective is to see that these conditions are avoided, like tensile failure should not happen, and as well as the pull out failure should not happen. That is the whole principle. And this is another example that we would like to mention, like what happens if you put reinforcement. Say for example, sigma 1 u unreinforced soil, and then this is sigma 3, and if you so this is at and then you have two circles actually, okay, both are unreinforced. So, what we say is that if you put confinement or reinforcement, it behaves similar to a composite. Earlier you have a reinforced soil of only for these two, it is a friction is there, which is corresponding to unreinforced soil, and by this process of additional confinement, what we have done is that there is a cohesion that gets developed, that gets mobilized, we try to say that, and it is called pseudo confining pseudo cohesion. So, like we introduces some sort of pseudo cohesion. Earlier it was only C is 0 and phi equal to some number, say 30 degrees. Now because of this, like the failure, the thing is, earlier that you had two circles. Now for the same sigma 1, you have a higher normal stress taking. I hope you can understand that. It is a sigma 1 without reinforcement. Now sigma 3 is same. Then what I did, I put some sort of reinforcement and I applied load. So it yields at a point called sigma 3, right? It yields at a point called sigma 3, and so how do you now I can get a tangent here, I can draw a tangent. So this extra confining, this is what is called C cohesion, you have this advantage. So for the same normal stress, it is able to, because of the higher, we are trying to represent the effect of reinforcement by this cohesion, that is what it means. Okay. What you are trying to do is that we are trying to characterize the effect of reinforcement, that is what we are doing here. Okay. Because if you are trying to design a reinforced soil, what is that, one understanding is that it increases cohesion. So in a factor of safety calculation, if you know how to calculate C using reinforcement, so C equal to 0, phi equal to 30, say it gives a factor of safety of 1.2. Then put C equal to 20 kPa and phi is same, then the factor of safety could be 1.8 or something, which means safe. So that cohesion you can calculate here. Okay. This is what earlier people are doing. So the advantage, people have realized that reinforced soil technique is going to be very effective. So it has three components. One is a reinforcing element, like a strip or a grid or a sheet or anything. Then facing units to prevent soil from erosion. It can be precast concrete panels that we see, metal sheets and plates, gabions, welded wire mesh, shotcrete, wrapped sheets of geosynthetics, anything. Then backfill soils, you have some specifications here that we will discuss. You can have local soils, marginal materials, even fly ash can be used. In fact, I have used fly ash in many of at least 2 projects. Why is it the technique has been effective? Actually, the thing is that we should see why the reinforced soil is effective, and from technical angle and as well as economic angle. In terms of the technical advantages, see, if there is a force, like it reduces the forces in the soil which cause failure, like there is a disturbing force and earthquake force acts in the opposite direction, which means that it reduces the forces in the soil which cause failure. The another important thing is that shear resistance of the soils does not dominate the design. Like earlier we had only C and phi. For example, if the C is not there, it is only a sandy material, it fails, that is it. Because if you just do any stability calculations, C will have a very big effect than friction between the two. Like in any stability calculation, use any slope stability program, you have to give C, you have to give phi, you have to give gamma. So gamma has a minimum not so much effect, but friction has good effect and cohesion has the highest effect. So but then suppose you take a sandy material, cohesion is very low, then it gives a problem, the factor of safeties are less. Now with reinforced soil, you are able to give cohesion, and now you see shear resistance of the soils alone does not dominate the design. We do not need to bother about whatever is the shear resistance available is okay. Now you are putting a reinforcement and increasing the shear resistance, that is an advantage to whatever you want. So that way the shear resistance of the soils does not dominate the design. Then efficient use of materials, say like the soil is poor in tension. So you are trying to mix or add some reinforcement elements which will make soil as good tensile force carrying materials. So you are trying to make an efficient use of materials which is called, say for example, the both soil and reinforcement, if you they have an excellent combination of properties. In fact, you must be knowing about in soil mechanics strain hardening and strain softening. If you put some sort of reinforcement, strain softening will not occur, I mean it reduces. Actually, we will see that in some later lectures. The thing is that there is a very nice combination of materials that leads to very synergetic improvement. Like synergetic improvement means in association with soil alone is weak, reinforcement alone you can't do anything like. So, by combination of these two materials there is an excellent advantage. Then the other important point was the inherent flexibility and tolerance to deformation. Because of this advantage, it is much more flexible and the earth pressures they get adjusted themselves, and there is a deformation tolerance is very high. See, in some cases the deformation could be as they can't, some retaining walls cannot take deformation, it may collapse, but here there could be deformation, but then it could stand. In fact, I was seeing one case where the height of the retaining wall is about 42 meters and the deformation that was coming was about 450 mm. 450 mm in a regular wall is impossible. Even the height of the wall is 42 meters, it is impossible to construct an RE wall with, I mean regular wall with 42 meters, because it needs heavy, I mean lot of concrete quantities and steel quantities are required. There is the reinforced soil technique is a very tolerant to deformation. So, reinforced soil structures are very useful. Then improved overall performance of the structure. In the structure performance is also overall improved. It is like I will tell you the classical example of pavement design. If you put some reinforcement in roads, definitely the overall performance of the road will be very good. Why? Because the way it acts, say for example, as I said, load distribution of the, what is the concept in pavements is that if there is a load, traffic load that is coming, it should be well distributed. So, how do you do that in the field actually is because you have various layers of materials that are putting, but instead of that you put a geogrid there, excellent, there is no problem at all. So, the performance is, it is number one, the thickness of the pavement has come down, number two, there is a overall performance of the say load dispersion characteristics and all, by somehow with this process it improves the overall performance, that is a very important advantage. Then of course, the economic benefits, like one is the cost savings related to other alternatives. Time and again people have seen that these techniques are going to be very effective and very economical. Then these will enable the use of locally available materials and poor quality fills also, like as I just mentioned, fly ash could be used, bottom ash could be used, any materials could be used, but one should do proper quality control tests and see that that is all right. The other one was the land acquisition cost. In many cases I showed in the previous case, like a railway line is there, land acquisition cost, and either side you have to construct big slopes, say for example 1:2 slopes, like 2 horizontal to 1 vertical, 1 vertical to 2 horizontal. If you just want a 10 meter embankment, 10 meters plus 20 meters on the other side, you have to say that 20 meters is required on either side of the road. And suppose you think that there are paddy fields, it is not, so paddy fields are gone, or if they think that there are buildings, it is not possible to do at all. So, what is the best way? You make it vertical using this technique, you do not need to really or make it whatever is tolerable, say for example make it 85 degrees vertical, that is nice. So, there land acquisition cost could be minimum, and the another advantage is less construction time on projects. Say for example, there is this as I said, it involves the use of precast elements, precast elements, everything fabricated, like in the reinforced retaining walls you have to queue 21 days and 28, there are a lot of other things. Here you have a precast elements which you bring reinforcement, you assemble, put compaction, and it starts, you can do very fast. I have seen many projects where the cost of construction is very well controlled, and you can accelerate projects to keep up the times that are specified. Now, what is the mechanism? Some more. What we saw is that we have seen some idea how reinforcement can be effective. We will understand it further. This is unreinforced soil slope. this is a shear resistance and the failure surface, and on the either side you have a it tends to fail, and then there is a resistance along this line and all that. Now you are trying to put a reinforcement here, 1 2 3, there are 1 2 3 4 5 6 layers of reinforcement, and they have an inclination at some theta degrees. Okay, you have to the failure surface, this is a failure surface, and then it is an angle theta, this reinforcements are placed. So how does it act? We have to see and quantify, we will see that. See, this is analogous to a direct shear box. You apply some vertical force, there is a shear force, right, and what happens, this is a soil without reinforcement, and in this soil element which is under shear, there is a compressive force, like because of this movement in this direction, there is a it is compressed in one sense, like, so there is a compressive strain, there is a tensile strain, like in this direction it is a tensile stress is acting, and in this direction there is a compressive stress acting, both are perpendicular. And how do you get the shear force? Shear force is nothing but, I assume that it is sand, C plus sigma tan phi, right, or P resisting force is nothing but PV tan phi. We know the friction angle of the soil, and like shear strength equal to sigma tan phi. It is not strength now, it is just a force only, because we know the area of cross section. So, we try to put as this. Now, what is happening here? If you put a reinforcement, what is happening? This is say the way that we put was, we are trying to put in the direction of tensile strains little bit, okay, because you have to, if you want to take advantage of the reinforcement, you should put in the direction of tensile force. So, I am putting in this direction, okay, then this is that angle whatever, okay. Now, what I am trying to do is that this is the shear force acting. Now, because of the reinforcement, so actually I have a PR reinforcement force PR in this. So, PR, if you just resolve into two components, PR sin theta, PR cos theta, you will get. So, the shear force PS, there is some opposite directions acting. So, the way that I do is that now shearing resistance for soil alone is PV tan phi, that we have seen earlier. Now, reduction in shear force is PR sin phi, as a sin theta, as I said, no, like this is a so you have to theta, you have to resolve PR sin theta, PR cos theta, you will get. So, what is the reduction shear force? It is PS is acting, but this much is reduced now. So, PR sin theta is reduced. So, it is reducing the forces, shear forces causing instability, like whatever is a disturbing force or the shear force, it is reducing by PR sin theta. Then the other one was, it is a PR cos theta, it increases the shear force, like say PV is already acting, say for example, there is already a load acting, you can't remove it, you can't shear it. Now, with this what is happening, you have a PR cos theta extra added. So, you definitely can't remove it, shearing, like say normal stress is acting, this is a shear stress, if higher is a normal stress, higher is a shear stress. So, if you apply more force, you can't remove it naturally. So, you have PR cos theta tan phi, okay, that you have to resolve into that angle. So, this is say this angle, right, tan phi in this direction of angle, okay. The increase in force causing shear, right, increasing. So, total shear resistance is nothing but PV tan phi plus this is an extra component that comes here. Now, because of this reinforcement action, PR sin theta plus cos theta tan phi, okay. So, tan phi, why is it tan phi? This is a normal force PR cos theta into, you are calculating the force, right, and so this is a normal force, you have to multiply it by tan phi to get into that shear force, right. So, PV tan phi plus PR, so this is actually the extra shear resistance you are getting. Earlier it was only PV tan phi, you are getting this much Now, you see that this is a function of theta, which means the angle and also the friction angle of the soil, right. So, we will just write a simple calculation like increase in shear resistance P sin theta plus cos theta tan phi and reinforcement orientation. So, what is happening here is that the best orientation is like you can see, you can plot like this diagrams, right, these are all principal strains directions. So, in this angle you can see that it is maximum, like it is in the range of say 1 or a little higher, whatever. You can just put some numerical values in these numbers, like you can put some numbers here, whatever numbers you want, and then like PR, PV, some reasonable numbers, and see that. So, you will get this sort of diagrams, and it only shows that the between 30 to 60 degrees the angle of inclination, okay, there is an optimum benefit, and it increases as phi of the soil is more, that is all it shows, like, so that is good. So, this particular thing leads to the condition that, say for example, it is a very interesting observation that say I will take the previous example. You see this even this particular inclination, what, so it will be in the same angle, the way that we try to do in the construction, like you are trying, if you place reinforcements in the while doing construction, they will be at an angle 30 to 60 degrees, the difference is not much, the angle is maybe say 40 degrees, that angle is always achieved. In the case of footing, how the bearing capacity is there, failure surface is like this, you put reinforcement like this, it intersects the failure surface in the same angle, roughly 30 to 40 degrees. So, what it means is that in many geotechnical operations, it is very easy, very nice to use this technique, like normally what you are doing in geotechnical thing, you just put a layer of soil and then put a again put one more layer and then compact it, put one more layer, compact it. But here what you are doing, okay, you are doing compaction, then put a layer of geograde, like say for example, there is a wheel load coming, under the wheel load the bearing capacity is less because bearing capacity failure surface is a log spiral, but if you put a reinforcement there, what happens, and then it will be actually having the same angle roughly 30 to 40 60 degrees, because the failure surface is like this, like a log spiral, and it intersects that reinforcement at that angle roughly, and you will have a maximum effect. So, for reinforcement applications of bearing capacity or even slope stability and many of these things, it is an excellent technique, because number one, you can do it very easily in the field, number one. So, for example, this is very important, how the ease with which the technique can be done in the field, because you do not need to change many of your techniques. See, I will give you another example. People have discovered that pre-stressed concrete is very useful in RCC construction, but the technique itself is so specialized. You will not have many pre-stressed concrete structures specialists, and you have an RCC specialist, suddenly you can't ask him to become a pre-stressed concrete expert. Here it is not so, ask him to put a layer of geograde extra and then ask him to compact, he is very happy, because you can tell him that yes, you are going to have a significant difference, and the project is going to be finished in a shorter time, and also that it can be economical. So, this is precisely the reason that this technique has been very useful in geotechnical construction, whether it is for the improvement of slope stability by nailing, reinforced soil, or improvement of bearing capacity and all that. So, in a simple say, it's yes, it is very useful. And one more, so this is precisely the reason that so for example, you can see like between about 40 degrees to about 60 degrees, whatever is that you have a failure surface, and then if you put a reinforcement, the angle is not in the same range roughly. So, that is an advantage. So, you will get a so this is precisely the reason why many people have embraced this technology without much reservations, and the advantage is that the three people who are very happy, contractor is very happy because the owner, first of all, owner is very happy because he has number one cost effective solution, then he also has, as just mentioned, technical advantage as well as economic advantage. Then the contractor, first one is owner is very happy, then the designer is also very happy because he is able to give some design now using this reinforced soil. You can simply has to say that yes, you put a reinforcement like this, you will have a good benefit. The third one, contractor is also very happy because he is able to finish the project very fast and it has been very useful. So, these three groups of people, if they agree together, then it is nice, right. So, before we go further, we should be able to understand what is this, you have now a backfill, right, soil is there and soil is to be compacted, because to have a very good effect the soil has to be compacted. So, this is a backfill soil properties, like we know that if you have a say normally we are trying to use sands as backfill materials in many of the flyover projects, and so loose sand will behave like this, okay, like it reaches a critical volume, critical state volume at this point. Then you have peak. In the case of dense, it is like this. This is what I was mentioning as strain softening, right. So, now this is in the case of drained. In the case of undrained test, you say you will have a pore pressure mobilized, this is the sigma 1 minus sigma 3 derivative stress. In the case of drain test, you will measure volume change also. These are all various types of stress strain curves that we see. What we need to see is the how both reinforced soil as well as how the reinforced soil behaves. And as I just mentioned, we have different types of reinforcement elements. One is called, one can be a steel reinforcement in the case of like a steel reinforcement or like a geogrid, like a steel grid, it is very stiff, stress strain properties are very good, stiffness is there. Then you have a geotextile, very flexible. Then geogrid may be in between, like it's a geogrid is much better than geotextile in terms of the stiffness. That is the reason why we use it in many of the applications. Even the steel also we use, like there are companies that only supply steel as a reinforcement. There are some companies which only supply geogrid as a reinforcement. There are also some companies which use a geocomposite, because sometimes you want high drainage in a drainage in some applications plus reinforcement. You have this, in fact, for one of the projects which I saw, I was mentioning about 42-meter high wall, they used a geocomposite which acts both as a tungsten material as well as geogrid material, right. So, so you have this material and you also have what is called properties of the soils. So, how do they match? This is very important because as I just mentioned, the performance of the reinforced soil is a function of the force mobilized in the reinforcement, is it not? Say for example, you apply some force, you apply some load and you have a reinforcement, this thing, the moment there is a force developed in the reinforcement, then it takes care of that load, like there is a one component of that load, the tensile force that comes into picture, it starts acting. So, how fast it can act before it takes more deformation is very important. You will see that here that as I said, in the case of loose materials, say for example, so you can know that you take a reinforcement, in the case of a stiff reinforcement, what happens, this is a stiff reinforcement here, this is a stiff reinforcement available force, available force in the reinforcement, right. So, like in the actually force, the way that force is developed is as higher is the strain, higher is the force in the reinforcement. Like say for example, a stiff strain in the reinforcement, the stiff, in the case of a stiff reinforcement, you need less strain to go to see that the force is mobilized, stress is mobilized in the reinforcement. So, in the case of a stiff material, you have a point here, right, which will have low strain. Now, you come to a flexible member, you have a higher strain level. So, for example, this could be say for example 0.1%, this could be 4%, right. This, so, but then what is this? This is like you have seen one more, what is this diagram? It is in the actually it is a loose, in the case of loose materials we said that there is a you have seen in the previous figure, right, dilation and the dilation. So, if you just compress a loose sand, it continues to compress, right, like 0.1 to say maybe 10% it continues to compress. Whereas, in the case of a dense material it is like this, the thing is there is an initial compression, then it starts increasing, right. This is what so this is an important thing. So, because of this what happens is that in the case of loose material the strain, say for example the say in the case of stiff materials this is a force, I mean this actually the combination of this this point, say in the case of stiff material and then this is a loose one, you have one point, this is another point, this is another point. So, we are trying to calculate the stress strain in the reinforcement as well as the strain in the soil, depending on the type of soil, depending on the state of the soil, whether it is loose or sand. So, this type of diagram is called strain compatibility diagram, and this is very important. Why? Because say you have a loose material, the reinforcement the resistance only comes the moment there is a contact and then the strain gets developed. So, in this case you can see that say you take this case these two, say in the case of dense material the strain required is marginally lower than this, there are small differences, like if you just draw two vertical lines here, this value is somewhat, this is a dense material, this value say maybe 0.2% or maybe 0.5%, this may be 1%. The strain required in the case of loose sand is little higher compared to that of loose dense sand. Here you can see big difference, like strain required in the case of loose sand is much higher compared to that of dense sand. The same is the case, particularly if it is flexible and if it is loose, it's you meet a lot of strains, but whereas here it is quite less. So, as high as, so this is an important advantage that if you compact it very well, you will have this sort of behavior. Do you know dense materials tend to dilate, right? When there is a tendency to dilate, and then you do not allow the things to dilate, what happens? The effective stress increases, is it not? The effective stress increases because of stopping of the dilation tendency, because there is no place for dilation in the reinforced soil. So, all are compacted and all that. So, that dilation it acts on the reinforcement. So, once it starts acting on the reinforcement, the more force is generated. So, you can see that the state of the loose sand or dense sand, whatever it is quite important, and also the stiffness of the soil is also important. So, this is what is called strain compatibility diagram, and this is very important in the analysis of reinforced soil structures. Particularly density, all specifications come on these lines. Okay. So, there are many techniques that people have been using in the actual construction, and I will show you some of them. And as I said, reinforced soil is a construction technique. Okay. It's and then the performance, I mean the reinforced soil, the way it behaves in the field is a function of how well you construct. If you do a hopeless job, definitely it collapses. Maybe the principle is very good, but it fails because if you do not implement it properly. What you should do, like say for example, there are different methods in the olden days, that too when the soil was developed, like this is called concertina method. This is one of the methods that is quoted in literature. Like you take some, they are all in sheets, you can have aluminum sheets or whatever sheets, because I told you if you have a reinforcement like this, the earth pressure coming on the facing is minimum, but then what happens, you are trying to connect the facing and the reinforcement, is it not? You have to connect it. So, because of that some force gets transferred to the reinforcement also. So, for which, say for example, there is so much tensile force. How do you calculate tensile force at any point is nothing but say for if geotextile you are using, geotextile has more tendency for deformation. So, I use Ka into sigma V will be the horizontal force acting, and suppose I am talking about SV is the vertical spacing and SH is per meter length. So, I am using say per meter length of the geotextile, Ka into SV into Ka into sigma V into SV will give me the horizontal force acting at any point, is it not? So, you know the spacing and you know the vertical stress is nothing but gamma into height. So, gamma B, you know, bulk density. So, you will be able to know what is the lateral force, and that much is a lateral force that should be generated by friction, so that it acts in the opposite direction. So, that much force you can calculate by this expression, like which I said Ka into sigma V into SV. SV is a vertical spacing. So, that gives a horizontal force at any point, and that should be equal to the tensile force in the reinforcement say per meter length of the. So, I said 10 kilonewton per meter or 15 kilonewton per meter, like what it means that okay, it needs that reinforced soil wall needs 10 kilonewtons in the opposite direction. So, go to the literature, such a material that has that property, like you take any of the geotextile material that you have, it will be say 25 kilonewton per meter or 50 kilonewton per meter, it is fine for us, because as I said, if I have a 50 kilonewton per meter and I only need 10 kilonewton per meter, then the factor of safety is 5 roughly in a working stress method of design. But then having that 50, you have a damage factor, then you have time factor for creep, factor for environmental conditions, factor for what I said the lifetime, all that. There are some 3 or 4 factors that we will discuss in the next class, that once you do all those factors, like say the 50 divided by 1.1 divided by 1.3 into 1.6, like that, you will get some number which could be say 15. So, that 15 is more than the 10 required, so it is fine. So, that is how we have to do the design, and once you are able to design at every step in some simple sense, then of course, there is lot of sophistication involved, but in a way the principle is that you must be able to design all the spacing and all the reinforcement like this, and I mean spacing of the reinforcement. The length of the reinforcement is again, as I said, you have a 45 minus 5 by 2 angle here like a failure plane. That length you had to again calculate the friction, you have already calculated tensile force, there much that frictional force should be, whatever is a frictional force should be twice of this tensile force mobilized, like as I said tensile force is Ka sigma V, I mean sigma V into SV, right. So, that is a tensile force. So, then you have to from the where it cuts, that the frictional area of the geotextile, like that you have to calculate per meter length again. If you are able to calculate friction force along the geotextile, if it is more than twice this, it is all right. That is how the simple design is done, and the way that it is practiced in the field is that you have a concrete panel facings and you have some sort of this thing here, like so. This is in some spacings of 250 mm, it is in terms of the compaction lift thicknesses, and there are different methods of doing that, and we will see more of this in the coming classes, because this is one technique that has made a very big impact in infrastructure, construction of flyovers and all that. Okay. This is another one that I would like to show, like say for example, you also have some drainage elements here, this is another method. So, you have even this can be a Gabion type of wall, you can put reinforcement like this, geogrids like this, is so flexible, and in the case of slope also it can be done like this. Actually you can have different types of facings, this is, we call it full height facing, like as I said in one case the way that we did was that we made some members, 2 members we put directly concrete into that, put joined, see the geogrid was inside this, then we had a shuttering like this, then put some RCC, just to have a facing. You can do a lot of things, and as I just showed the other day, you also have what is segmental blocks. Segmental block means, see, this may be a big height panels may be difficult to handle, but you may have a simple what is that it's interlocking concrete wall blocks, which can interlock, and to one fellow can lift it and put it, the other fellow will take the reinforcement and stretch it, then you compact it here, then again one fellow will put this and then put this, and like this, they keep on doing it, and then you do whatever you want. So that is it. So once the design is complete, essentially we are looking at the set pressures and all that, it is very safe, because safety is very clear. I showed you that fundamental principle in which as long as a forces are within the below the yields of the whatever that failure surface, it is going to be safe. So you have to properly look at some of these fundamentals, and you can one can construct, is it not? So this is what I meant to say, and I am sure that this is one technology that has revolutionized the cost of infrastructure. In fact, in ground improvement projects, say for example, you are constructing an embankment in a soft soil, like earlier we were using stone columns. Stone columns are being used still, but you put a geogrid at the top or bottom, it helps a lot. Even in a stone column, you can put what is called encasement of say, as I said, we know the failure mechanisms of stone columns, in which there is a bulb formation and all that. You put some sort of a confinement, the bulb will not form. The bulb, if it does not form, it is very good, because bulb formation is because of its failure mechanism. If you do not allow the failure mechanism to take place, it is an excellent thing. So like that, it has even for PVDs and many ground improvement projects, it has taken even geocells will discuss, it has really impacted in a big way. Thank you.